In chapter 18, we're talking about the kinetic theory of gases. So we're talking about what's happening more at the atomic level rather than on the macroscopic level. There's a couple of equations that we're going to look at. One of them is called the mean free path. It's basically the average distance a molecule will travel before it runs into another molecule. Your book uses a lambda to represent it. The equation 1 over 4 times the square root of 2 times pi, the pi is not under the square root sign, times the quantity n over v. Capital N means what? Number of molecules. Capital V, volume. That ratio is the number of molecules per volume that you have. Okay? It's called the number density. So number of molecules you have per volume. And then R is the average radius of your molecule. Your book gives you some approximate values that you're welcome to use. Again, it's going to depend upon whether your gas is monatomic or diatomic.
Trina?
Yeah,
Little n's moles and big n's molecules, right?
correct. Little n is moles, big N is molecules. That is correct. So for gases, an approximate value of R, if you have a monatomic gas, R is approximately 0.5 times 10 to the negative 10th meters. If your gas is diatomic, then it's about twice that, because there's two atoms bound together. So the mean free path is the average distance a gas molecule will travel before it hits another object. You can certainly use it for anything. Any objects confined to a container moving around. Mean free path is the average distance before they collide with each other. The other equation we're going to look at is the actual energy that the molecules have. So kinetic energy. We know kinetic energy is 1/2 mv squared. Not all of the molecules in a gas will actually be moving at the same speed. There's a variety of speeds. Some of them will be moving slower, some of them will be moving faster. So when we talk about kinetic energy, we're going to talk about an average kinetic energy. So the average kinetic energy that our molecules have. Turns out, because the speed is squared here, we're going to be taking the average value of the squared values. When we take the square root out, so when we take v squared and we average it, if we were to solve for v, we would end up square rooting it. This is called an RMS value. Root mean squared. We squared it, mean, we found the average, and then we square rooted it. RMS. It's not a true average, but we treat it as if it were an average value. So in this equation, this V right here is going to specifically be the RMS value. The average kinetic energy will tell you the RMS speed of your molecules. M is the mass of your molecules in kilograms. So if you have an oxygen molecule, you need to look on the periodic table. Oxygen is 16 U. Oxygen gas is 2 oxygen atoms bound together, so it's going to be 32 U. And then you need to use the conversion between atomic mass unit and kilograms to find out how many kilograms it is. Your book goes through a derivation and comes up with an equation. Make sure this is right. I'm not going to bother going through the derivation to get here. The pressure of your gas basically depends upon the number density, depends upon how many molecules you have in that volume, depends upon the mass of the molecules, and on average how fast they're moving. Okay. What I would like to do is to relate these two equations to figure out what kinetic energy actually depends on. First of all, I'm going to bring the V over. I'm going to bring the 3 over. And I'm going to divide by N. So that all I have is mv squared on this side. Kinetic energy, though, is 1/2 mv squared. I can legally put a half in on the right side if I put it in on the left side too. So what this tells me is that the average kinetic energy of my molecule is equal to 3 PV over 2N. So pressure and volume and number of molecules determine kinetic energy. But ideal gas law, in terms of number of molecules, PV is equal to the number of molecules times the Boltzmann constant times temperature. PV over N is simply the Boltzmann constant times the temperature. So the average kinetic energy is 3/2, still the 3/2. In place of PV over N, I'm going to put the Boltzmann constant times the temperature. That tells us the temperature is the ultimate determining factor of the average kinetic energy. The hotter the gas is, the faster the molecules will be moving on average. The colder it is, the slower they'll be moving on average. This also means if I have hydrogen gas at room temperature, if I have oxygen gas at room temperature, if I have helium gas at room temperature, if I have any gas at room temperature, the average kinetic energy is going to be the same. Okay? Their speeds will not be the same though, the average speed. The average speeds will be different. To figure out speed, we can set this equal to the 1/2 mv squared. Oops, mass doesn't cancel. Sorry. The 1/2s cancel. The RMS speed, so what we're treating is the average. On average, the molecules how fast they're moving will depend upon the temperature of the gas and the mass of the actual molecule itself. This is the speed of one molecule. So you need to know the mass of one molecule and the temperature that the gas is at. Now actually, just so you know,